And we are off. Welcome, everybody. This is the gRPC Community Meetup. My name is Maria Cruz. I'm a program manager in the Google Open Source Programs Office. And we are going to start this meetup. I wanted to have a general question to the community to ask if there's any updates for the community before we jump into the demo. Anybody or any working groups that may have updates, now would be a good time to share them. Okay, so we are going to move forward with the meetup. We have here with us today Animesh Chaturvedi, who works in the Palo Alto Networks, and he is going to present large-scale ingestion using gRPC. Animesh, you should be able to share your screen, so go ahead whenever you're ready.
All right, thanks, Maria. Okay, do you guys see my screen?
Yes.
Yes.
Yeah. All right, so good afternoon, folks. Thanks for inviting me to this gRPC meetup. This is sort of a talk that I had given at IstioCon, and Maria reached out, and then Romina reached out to me to ask me to come and share our experience at Palo Alto Networks using gRPC. So here I am, and thanks for inviting me again. So this is not really a demo. Demo requires a bunch of setup and is not available to be shown here. So I'm going to mostly talk about my experience and how we are using gRPC. So Palo Alto Networks, as you know, is a global cybersecurity leader, and we have many products securing network, cloud, and security operations. And data is very important to understand what is going on and stitch best of breed solutions. And as such, we were building a massive data lake in early 2019. And since we were building this data lake from ground up, we wanted it to be cloud native, API driven, massively scalable, multi-tenant, and so forth. And for the most part, this data lake receives data continuously from Palo Alto firewalls and applications. And as such, we were evaluating between sort of a RESTful request response based communication versus streaming. And gRPC pretty much came up at the top, given that it supported a bunch of different communication modes. And in order to support a high level of ingest, several 100 billion events per day, the cost was also a big consideration. So it's technically possible to build a system which, even based on HTTP REST, which can scale to that level, but it's going to be a lot more expensive and costly. So as a result, we started looking at gRPC and giving a high level overview of what our data lake is and how our customers use. This is sort of a high level architecture. Our customer buys a virtual data lake by going to an onboarding portal at Palo Alto Networks. When they buy a particular a virtual data lake, we basically provision a bunch of systems behind the scene for this. This is a completely multi-tenant pipeline. So once a customer has bought a virtual data lake of certain capacity, we provision the backend storage, we provision our internal components to support their needs. And then there is, on the top left, you see are the producers. These are typically our firewalls, Palo Alto Network firewalls, or applications producing data to this data lake. So we support TCP, which was our sort of proprietary binary protocol, and this has been around for a long time. And since we were building a new data lake, we decided to try out gRPC, especially in the bidirectional streaming mode. And in the middle are the consumers. These consumers are basically consuming this data that is stored in the data lake. And there is HTTP REST API to be able to query the data that is stored in the data lake. As a data lake, our footprint in terms of API is rather small. We have some provisioning and onboarding APIs. We need to provide an ingestion API to be able to ingest data. We need to be able to provide a query API to be able to query the data that is stored in the data lake. And then we need to support stream and batch compute on this data. So that's how we started. And I'll quickly go over gRPC. Most of you, being part of this meetup, are intimately familiar with gRPC, so I won't spend too much time on this. Basically, it was created by Google. It uses HTTP2 as its transport protocol. It allows full duplex bidirectional communication, and it has very good flow control capabilities provided via the underlying HTTP2. So how do you really implement a gRPC client or server? So in this context, I'm mostly going to focus on the Java side of gRPC, the gRPC Java implementation. So the client and server, they both implement a stream observer interface for sending and receiving messages. This interface is rather simple. You have only three methods: on next, on error, and on completed. So when a client starts sending data, they're gonna write to their request stream, and on that they'll implement on next, on error, and on completed. So for outgoing messages, this stream observer is provided to application by the gRPC library, and the client will start writing through that observer. For incoming messages on the server side, the application implements the stream observer interface and passes it to the gRPC library for receiving data. The main thing that we were evaluating at that time was to look at different streaming modes. So we were comparing unary and bidirectional streaming modes in gRPC. And for unary mode, the throughput is relatively low. Bidirectional gives you a very high throughput. Latency, likewise, is also high for unary, but bidirectional has very low latency, low overhead. And the main differences between the item number 4, which is RPC call, is synchronous for unary and asynchronous for bidirectional streaming. So the pros and cons are listed here. And with bidirectional streaming, the message throughput is higher and latency is lower, which met our requirements. And our firewalls are typically connected all the time, so it did make sense to go with the bidirectional streaming from that perspective. Now, having long-lived streams and multiple messages per stream using bidirectional streaming does transfer some of the responsibility of flow control, etc., to the underlying application. And that's where we ran into some challenges, which I'm going to cover in the next few slides. So this R pipeline initially worked pretty fine without much tuning, and we were able to ingest about 10 billion events per day, which is still a significant number. But uh, but as we progressed and added more load, our pipeline got stuck, and we used to have cascading failures. And there were several issues, and one of which was gRPC. So I'm going to talk a little bit about the other issues and stay focused more on the gRPC side. So at high load, we basically ran into some issues in terms of the infrastructure that we were deployed, which is a cloud provider. We use Google Cloud, so we had to do some tuning on the GKE node kernel side. There were implementation issues in the Istio side. We were also one of the early adopters of Istio at that time. And that decision was driven mainly because we were using gRPC. gRPC, since we had already selected gRPC, we were looking for proxies that supported gRPC natively. And Envoy was the only proxy at that time in beginning of 2019 that supported gRPC. So we went with gRPC, Envoy and Istio at that time. So what we found out was basically we needed a large number of pods in order to scale, and we had some challenges in controlling the back pressure and the flow control. And that's where we found out we had to do some work. So first, we had to exert flow control. And the way this gets done in gRPC is, as I had mentioned in one of the earlier slides, maybe let me jump back to that slide. So the client and the server implement the stream observer interface, right? So on the server side, if you want to exert flow control, the way you will do that is delay reading your on next. And that way, the buffers in between will start getting filled up. If the server is not reading from this channel, it's basically will slow the responses down to the client. Okay, so exert flow control. And this is another important point was we are deployed in Kubernetes, and we wanted to leverage Kubernetes horizontal pod auto scaling, and the default long-lived gRPC connection hindered our ability to use horizontal pod auto scaling, and I will cover that in just a bit. So we had to implement a connection expiration policy in gRPC, which is actually configurable via just some configuration parameters. You do not need to make any code changes. Now, it's not just enough to exert flow control on the server side. On the client side also, you need to do a bunch of work to be able to adhere to those flow control messages. And for that, in 2019, the version of gRPC, I don't remember the exact version we were using at that time. If we look at the documentation, the uh, the flow control capabilities were marked experimental. So there are two ways to do it. You have on-ready handler, and so this is basically when the underlying channel is ready, you will register a call back, and you will basically get a notification, and then you can start sending data on that stream. And another issue we ran into, which was more of a manifestation of how we had implemented our client, we were creating large number of streams and connection, which was overwhelming our Istio and our upstream applications, because there were simply very large number of streams, and each stream carries data on it and has some capacity in terms of memory. And if you have very large number of streams, your parallelization is is too much to handle, and it was not really the way it was designed to be used. So we ended up fixing both the server and the client. And talking about back pressure and flow control again, in systems, back pressure is communicated by using buffers. So as in our pipeline, we had gRPC clients. They were talking to an API gateway. That API gateway was a proxy which would proxy the request to our upstream service, and we were using Istio and Envoy, and so there was a sidecar also injected as part of our workload. So if you look in this diagram, there are multiple buffers. On the left side, in the orange box, is the gRPC client netty buffer. Then there are two buffers on the gateway, inbound and outbound. Then on the sidecar, which is the Envoy proxy, has also two buffers, inbound and outbound. And on the right-hand side in blue is our netty server, which also has a buffer. So, so when the server is slow or it has too much load, if it stops reading or temporarily stops reading from the stream observer, these buffers will start getting filled up. And as these buffers get filled up, the client, when it says register the on-ready handler, uh, it will get called very less frequently, as a result exerting this back pressure. So it is in gRPC, it is important to tune these buffers as per your application need. And in our deployment, Envoy, which is being used as the gateway and the sidecar, per gRPC stream buffer value was very large. It was 256 MB. So imagine that you have large number of streams coming from the clients and being processed by these ingestion pods. If the ingestion pod for some reason becomes slow, these buffers will start getting filled up. The bigger the size of the buffer, the longer it will take to build up. And since these buffers are on a per stream basis, if you also have large number of streams, you may end up uh, going out of memory on any of these.
Well, I don't know what's going on there with this thing.
Do you have a question? Okay. I'll go back to my slide.
Mr.
Sorry for
Stringy.
interruption. Okay. So I'll let me start one more time. So basically, these buffers you need to control how large these buffers should be so that you can communicate the back pressure to the client quick enough. So we ended up tuning these buffers down. The client buffer are basically Java netty controlled, and they are by default at 1 MB. So we tuned them down to just 64 KB. And these Envoy buffers, which are 256 MB and were the primary cause, were also tuned down to 64 KB. And as a result, as soon as these things buffer fill up, the client will slow down and will help stabilize the pipeline. Okay. One other challenge we ran into was our load varies from in a ratio of 1:2 for min to max. What that means is during the nighttime, our traffic is, let's say, 1. During the daytime, it will be twice. And it is at our scale, cost is very important. So we wanted to leverage Kubernetes HPA or horizontal pod auto scaling to add our ingestion workload pods, and as more traffic comes in, the basically we wanted to add additional pods. This, however, does not work well if you have if the load distribution across different gRPC stream is non-uniform. And what we found was there was a wide range of variations across these pods in terms of how much CPU utilization they were working with. And there were like hotspots. Some pods were, if they somehow happened to get streams that had huge amount of data, they would run very hot and sometimes run out of memory. And we could not really leverage Kubernetes HPA. Kubernetes HPA relies on average of across all your pods to basically add additional pods. But if the variation across the pods is very high, it may not even rise up to an average value, which is whatever threshold you have set to. So it is important to narrow the band for a more controlled and uh, uniform auto scaling. So in order to do that, we had to control the gRPC connections. If the connections are long lived, they would basically get pinned to a specific upstream pod and start sending data to it, which would result in hotspots. So we had to control the gRPC connections. And for that, in case of Java gRPC library, this is done by using two configuration server builder options, max connection age and max connection age grace. So what this means is the server will allow the connections to go up to max connection age, and it will not allow new streams to be created, but it will allow existing streams to continue until that grace period option. So we played with bunch of different options to arrive at based on different load, arrive at values that would work with us for us. And after that period, the connection gets expired. And for the auto scaling portion, we ended up tuning our stream duration so that by these two measures, we were able to uniformly spread the streams across the pods, and we achieved very good horizontal pod auto scaling. So after all of these changes, we basically were able to run our pipeline. We currently process few hundred billion events in a day, and we have been growing very quickly in last year or so. And since this 1 year, we really didn't have to touch our pipeline. HPA kicks in, gRPC works beautifully, and we are able to continue to grow and be horizontally scalable. So, sort of that's all I had in terms of my presentation. If you have any questions on a specific slide or a question in general, I can take those now.
Hey, Animesh.
Yes.
One of the things you mentioned is not well documented. So something about gRPC advanced use cases are not well
So,
documented. So what would you like to
so
see, like some
actually,
kind of a white paper? Yeah.
I would like to clarify that. Basically, the on-ready handlers was marked as experimental. So we were not sure in the Java doc when we looked at it that it's experimental, that we could leverage it. So we ended up talking to Eric Anderson, who's the gRPC Java lead, and he gave us some insights on how to use that library. I know now that feature is no longer marked experimental. Modi, does that answer your question?
I was just, I mean, so was that the only documentation flaw you saw, or is that something more you would like to see, like in
No,
terms of
no,
how to use?
actually, that was the main one, and we got thrown off because it was marked experimental. We didn't know that we could use it. If it was not marked
Okay.
experimental, I would say it was pretty much up to the. It was good, but because of marking it as experimental, we were not sure we could leverage it. And maybe it made sense because not everybody runs at that scale, and it was working fine for us until we crossed like 10 billion events a day.
I think Fidel had a question. Fidel, would you like to unmute yourself?
Yeah, thank you, Maria. So happy to hear. So my question is regarding on when you are adding new pod that those pod get scaled back and forth. That configuration that you mentioned regarding the long live connection will ensure that the load will get evenly
That's
redistributed.
correct. That's correct. So if I go back to my slide, let me show you a previous slide. Now in this slide, you can see if you look at the bottom, right? Let's say, and we were starting like this test we did. This is like a really old data now. This
Yeah,
test was done when we had pretty much 0 pods. So you can see that the first pod that came up took in about 10,000 requests per second, or actually 11,000 requests per second. And each of these colors are indicating a new pod that joined the pool of pods in this deployment, right? So you can see the first few pods, they're going to run hot. They are handling quite a bit of requests per second. Their CPU utilization uh, would be high, and
yeah,
the HPA, or the average CPU utilization across pod, would be like, in that case, I think our threshold was 70%, would rise up. Kubernetes would add an additional pod, a new pod will come up, and you can see that over time, these pods started, the load across the pods started averaging out and come closer to about 5 to 6K.
I see. Cool. I have just a last or question. You mentioned that you are using Istio, or you guys are using Istio in this.
Yes.
Are you looking to any other like Envoy or similar to make
So is
comparison regarding the use of gRPC?
actually Istio and Envoy work together. Envoy is really the underlying proxy, or the data plane, and
Yeah.
Istio is providing the control plane. So we are using both. We have to
Okay.
use both.
Hey,
I have
Animesh,
one question. Sorry. Yeah, this is Sumant here. So I'm wondering, like, how many clients and how many server pods, the ratio you have for your use
Uh,
case?
so it really depends. So there is one more problem which I did not cover in this slide, but actually maybe I can talk about it. So in our pipeline, while we handled the gRPC load balancing issue with connections and by tuning the stream duration, what it also means is the data that we receive in our data lake is coming from multiple tenants, right? So over time, a given pod will be handling data for multiple tenants, right? At any given time, you can have data with multiple tenants coming in. our upstream is Kafka. So if I go back to one of the earlier slide, building a data lake. So once the data comes to the ingestion service, it's all multi-tenant. This is where our gRPC server lives. These pods are scaling up. And as these streams get terminated and new streams get created, these pods will end up pretty much seeing any tenant in the system. And as a result, we will create a large fan-in for Kafka. So we had to do a bunch of tuning on the Kafka producer and on the broker side to support our load. So while we did achieve our scalability we wanted, but we became a pretty much a large fan-in client for Kafka. So we had to tune it quite a bit.
How many messages you are processing per second, like a approximate throughput and latency?
So we handle few million messages per second, so which is like few 100 billion events a day.
Wow, okay.
Hi, Anish, this is Murli here.
Yeah, Murli.
So I have two questions. You said like you have limited your request based on duration and based on number of streams. So like what options did you use to limit it?
So let me clarify. So in gRPC, you have a connection, and then you have streams going over that connection. So we had to control the connection as well as the stream duration.
So like what option did you use to limit the number of streams?
The number of streams is actually limited by the client. In terms of duration, let's say a client is creating a stream to send data, and in our use case, we found that 500 to 1,000 requests per stream provided us the best performance in terms of distribution across the pods. But it could vary based on your own application. It really depends on how much time an upstream service is processing the request. If upstream is not doing much work, your throughput would be much higher. And it also depends on whether you need acknowledgement or not. Acknowledgement means that if the client has sent a request, the server needs to acknowledge, and only then the clients will send next set of requests. This ends up tying resources on the server as well as the client side and limits throughput, which is how, in our case, that was our requirement. We could not afford a data loss. So we had to ensure that the client and server are acknowledging. But if in your use case, if it's, let's say, a workload which requires more of an analytical workload, in that case, you may get by only doing client streaming and server doesn't need to acknowledge. In that case, your throughput would be much higher.
Sure. So my next question is about the load balancing. So it's mostly like connection based, right? It's a long-lived connection. So once the connection is gracefully shut down by the server, how does the client know it has to connect to a next set of like IP addresses? Did you implement any load balancing on the client side?
So that is actually handled by the gRPC library itself. We did not end up needing to do anything about it. All you needed was the FQDN of the server. And if the server, in this case, the server terminating the connection, the client will would need to had a connection pool, and it will basically pick another connection out of connection pool and start sending on that one. And the underlying gRPC library takes care of all of this.
So like by default, I know gRPC supports, I think the first IP address, right? It picks up the first IP from the DNS resolver. So you're saying like it's doing a round robin and picking up the next IP address?
I'm not sure we ended up tuning it, but we did see that our stream, like let me go back to the slide where we talk about. Okay. So no, not this one. So in this slide, basically there is an indirection happening. The firewall or gRPC applications are talking to the load balancer, which is really Envoy or Istio. And then there is an and then a new gRPC stream gets created by Envoy for upstream ingestion service.
Okay.
So we did not see any issues in distributing the connections across these load balancers were pretty much uniform, but it was mostly about the streams carrying varying amount of data causing hotspots.
Okay. So let's say if I have a network load balancer like in AWS, which is just a set of IP addresses. Does the solution work with a connection-based parameters, or do I
So
need?
I'm not directly. I didn't have experience running it on AWS, but we were using Google Cloud, and the NLB. We didn't need to do any configuration there. Basically, the client was given an FQDN, and that FQDN would map to a virtual IP. Behind that would be a bunch of, let's say, the gateway pods or Envoy pods, and we didn't have to do any other tuning.
Okay, so even
just an FQDN worked.
Even in GCP also there's like a ILB, right? Internet load balancer.
So yes, so there is something called GCP NLB, and NLB in this case is really a pass-through. The SSL connection termination happens at Envoys behind the NLBs.
Okay. Sure. Thanks a lot. Thanks.
So is that gRPC client is a Java client or
so gRPC client is a Java client. We also had like one of these application is a Java client, and the firewall gRPC client is Go based, and there are subtle differences between the Go client versus the Java client. Java is fully asynchronous. For Go, the Go gRPC library is blocking, and that required us slightly different tuning in terms of these stream buffers. So in case of Java, we were able to get by with a smaller buffer size because it's completely asynchronous. If you are using a Go-based gRPC client, it's blocking. So for that use case, we had to increase one of these buffer size. Otherwise, the client was blocking very quickly. So we had to tune a little bit more for a Go-based gRPC client, even though our server is all Java-based.
There's a question in the chat from David Bryson. David, would you like to unmute yourself?
Sure. Thanks for the talk. It was really great. Couple of things. One, can you put the link to the Medium post in the chat, because it's a link in your presentation, but we can't click on it.
Okay. I'll send it to you guys.
Thanks. And the other thing is, can you talk a little bit about the traffic pattern that you were tuning for? So I would venture a guess that if you're tuning this buffer size for 64 kilobytes with such a large number of connections, that your data volume is quite small but high in frequency. Is that a generally good description? Yes,
that's correct. So most of our requests going in a stream are below 1 KB. And it really depends on how quickly you want to sort of communicate back to the client that they need to slow down. So if you can, and the thing is, if you do not slow the client down or don't provide them the signals, and if you have large load, your server can blow up, right? So whatever suggestion I'm giving, you will have to tune it as per your own load and requirements and how fast your upstream server is processing. And this comes after trying out of various scenarios. First, looking at let's say a single server pod, and see at what point it starts breaking, and that gives you a baseline. And then from that point onwards, you can start adding additional nodes. And there is a comment from Sumant on, is this project also related to your work? Yes, that's the Medium link that's also put in my slide. So Sumant, looks like you found the link anyway.
Okay, thank you.
I mean, this is Lakshmi here. I have a quick question. So I was read your the article, and very nice, and I was trying to implement it in my company, but I could not make it work in the data flow, the client side, especially the client side. Do you have any like remove all your proprietary stuff? Do you have any sample program which you can put it in the GitHub? Is it possible?
So I can take that as a comment, but there is a post written by one of our engineers, and I'll maybe after this email, this
That was
session, I
purely a
can.
pseudocode. That was purely a pseudocode,
Okay.
which is not. I mean, if you try to do that in data flow, it's not working that way. So I replied to that message also. I mean, the post.
Okay. So let me take that as an action item. The main issue with data flow was, and that was one of the reason we ran into issues, was our client in this case was a data flow or Apache Beam application, and it was creating very large number of streams.
Correct.
And that's something you want to control, and you need to control the splits that are happening in your Beam application.
Yeah, to control the flow streams, we were using the semaphore and the semaphore type to control the flow control on the front and the reading itself. But the observer and the stream observer on the data flow, we are not sure how that exactly implemented. I tried to get it in the gRPC examples also. There was not such thing for the data flow, so that's why. If you can share one sample code, it'd be great.
Okay, so the stream observer itself is not that complicated, but I'll try to find get a snippet for you. And it was more about basically controlling the data flow splits.
Mm-hmm.
And so to give you some perspective, we had exactly the same problem, and we were generating very large number of streams. And and you can see that if you have 256 MB buffers and you have, let's say, few 100,000 streams, you're gonna really blow up in memory very quickly.
Okay.
Right. So let me find something for you, and I can reach out to you.
Hi, Animesh. Srini here.
Hey, Srini.
Hey, great presentation. And congrats that this system is running flawlessly for more than a year. You said, right?
It's been running for almost 18 months, and Eric is not on the call, but I really want to acknowledge that. I
joined late.
Oh, Eric. Okay. So this we actually got some help from Eric in terms of guidance on this gRPC tuning, and really helped us out. Thanks, Eric.
Yeah, and I hope in the future people might not need to do quite as much tuning because Java now has the bandwidth delay product automatic tuning for some of these values, like the 1 megabyte value right now. It still starts at 1 megabyte, but it can go up from there. There's some hope that we might be able to reduce the default so that by default, it wouldn't just consume as much memory unless there were some network conditions that would really benefit from it.
Okay, that's good to know.
Do you keep upgrading your gRPC version, or?
We actually didn't upgraded it just once. We haven't done it yet, so maybe it's a good time for me to go back and read up on the release notes for gRPC and try it out in our dev sandbox. Are there any specific features added in last 18 months or so that are significant enough for us to pick it up?
I guess the BDP change that Eric just talked about is one.
So the BDP change will actually be disabled whenever you use the flow control window API. Let's see, is that right? There's two flow control window APIs now. One of them disables it, and then one of them just sets it as sets the default value. But I don't think in your environment, in most sort of data center environments, you don't need as large of a buffer size. So I don't think it would impact things too much. You might notice that maybe the buffer is increased from 64K to 128K or something like that, and you squeeze out a little bit more performance, but I don't really expect it. I think I think mainly the improvements have been around some error handling, just making better error messages, and small bug fixes that sort of, those accumulate over time.
Okay.
But I don't think anything, I don't think you'll see a big difference, but it is good to stay halfway up to date.
Okay. Okay. Thank you.
Yes. Is the flow control built into the gRPC is the only way to control the flow, or is there any client-side throttling or server-side throttling anybody using?
So the client gets communicated that the server is slowing down, and a well-written client will adhere to those messages and slower its sent to the server.
Will it apply to the unary services also? It's only for...
Unary service is synchronous. So you're sending a request and you get a response back, and you're blocked until that time. But I was not using unary, so I'll let Eric comment on that.
The flow control just applies to the streaming calls. With unary calls, you have to do other sort of more classic approaches of either fail the request and have the client do some sort of back off, and you may even tell the client how long to sleep, or you not do a tar bit, but you would add in extra latency and delay to slow down the client a little bit. But those are pretty classic for pretty much any system. They don't relate specifically to gRPC as much.
Okay. Animesh, one more question for data flow. So for streaming client connection, the channel, you create once and then you send messages for every processing element, processing unit.
Sorry, I didn't catch your question. Can you
in the
repeat
data
one
flow
more time?
side, are you creating the channel one time for the worker, and then every new message you are pumping to that same channel? Is that how it works?
Yes. So we have like a connection pool, and you'll basically send to one of those channels. When the server disconnects a particular connection, I think gRPC takes care of creating basically a replacement connection underneath. So you don't really need to bother about it. Eric, is my understanding correct?
Yes.
All right. Before I let you go, and in case there aren't any other new questions, I wanted to direct your attention to the icon that is right next to the chat box, which is 3 shapes. There's a poll active there. So if you could give us your feedback through the poll, that would be great. And I'm launching another poll right now. So these surveys really help us to improve the meetup every time. So thank you for taking a couple of minutes to fill those out. And I saw some comments on the chat box about other people also using gRPC. So if you would like to show your implementation of gRPC, please do get in touch with the Google group that we have. I kind of blanking on the name right now, but I think it's gRPC-io@googlegroups.com. Checking that. Yes, that's the email address. So please email there with your presentation idea, and we can also feature your implementation. And yes. I just pasted the email address on the chat box. So if you can let us know there, we will be happy to also feature your work. And as I said before, this recording is going to be available on the gRPC YouTube channel. And once again, thank you so much, Animesh, for presenting, and yeah, everybody else also for engaging and for bringing your questions and comments to this event. It's really what makes the community meetup thrive. So thank you.
All right. Thanks, everyone.
And we'll see you next month. Gracias, Fidel.
All right. Thanks.
Bye, everyone.